Hey guys, long time ago people started trying to figure out how they could get machines to do work for them. What you see in the picture is James Watt's steam engine. You see the date on there, 1774, and somewhere back there is about the beginning of the modern age, if you will. All of a sudden we had textile plants and tractors and cars and things that would do work for us because of our understanding of the laws of physics. And there's a set of those, a subset that's called the laws of thermodynamics. And so I wanted to talk to you about that today. When we say thermodynamics, it's a big word because it's a big subject. It's the branch of physics that deals with the relations between heat and other forms of energy and the conversion of one into the other. Now, don't forget that work is a form of energy, right? Remember that we said that if you had energy, you could do work, or if you did work, you could generate energy. And there was like the two sides of the same coin where we could just kind of go back and forth between the two. So work's included in there too. Specifically, we're interested in how heat, temperature, pressure, and volume interact to produce work. So again, coming back to work and how can we get machines to do this for us. There are three laws that I'd like to talk about. Unfortunately, they made the first one first, the first law of thermodynamics, and everybody said, well, that's pretty good. And then they came up with the second law of thermodynamics, and they said, yeah, that's good too. And then somebody said, you know, we should have said this other thing first. And they said, well, what are we going to do? We've already got 1 and 2. And said we're going to have to call it zero. The zeroth law of thermodynamics is that two objects that are each in thermal equilibrium with a third object are in thermal equilibrium with each other. Now that seems like a silly thing to say, but it lays a groundwork where we can understand that these are quantities that can be measured, and I can compare the two. For example, if I take a thermometer and I stick it in a beaker of water here, and it says 80 degrees, and I take it over here and I stick it in the water and it says 80 degrees over there, then I feel pretty comfortable saying that this is in thermal equilibrium in the same temperature as the other one here. In mathematics, we would call this the transitive property, and people would write if A equals B and A equals C, then B equals C, or something like that. You could write it other ways, but you get the idea, right? I've got two things. They're each in thermal equilibrium with a third object, in this case the thermometer, and therefore they have to be in thermal equilibrium with each other. Boring. Next, first law of thermodynamics. This is the big one right here. Okay, this is the one that we're going to use more than anything else on the thermo stuff that we do here. So check this out. We really, really believe in conservation of energy. And in fact, remember, we have glorified that idea by calling it the law of conservation of energy. There aren't a whole lot of laws in physics, science. But this conservation of energy is a big deal. And it basically says you can't get anything for free, and you don't lose it either. It might get scattered and turned into something else, but it's still there somewhere, right? So when I start with some energy, I'm going to end up with that same amount of energy, and work is one of those forms of energy, so it's all got to add up. And this is probably the best way to write the first law of thermodynamics that I know of right here. Q stands for heat, and when I put heat into a system, it's either going to turn into internal energy, that would be the temperature and the pressure and the state, how much energy those molecules inside the gas or liquid or solid or whatever this is, they're going to be moving, vibrating more, or I'm going to get some work out. Right? If I have some energy, it can either go here or there, but it can't disappear, and it can't turn into 6 times as much or anything like that. It's got to add up. This is basic accounting here, And if you put 100 joules in and you get, you know, the temperature of something goes up by 80 joules, well, then you got some work out too, and it's got to be 20 joules. It's got to add up there. There's no mystery. There's nothing complex about this at all. It just has to work. Now, sometimes with conservation of energy, I like to think about money. If I have $20 in my pocket and I go to the store and I buy $6 of apples, then I've still got $14 of cash and $6 worth of apples, right? It has to add up, and this is exactly the same way. There's a little picture, a little diagram over here that we draw to represent that. Up here, the red is the hot side. Sometimes we call it the hot reservoir. But I've got some reservoir. Come on. I think that's right. And then the blue down there is going to be the cold side. And the reason there's a hot side and a cold side is because we know that heat travels from hot to cold. Cold reservoir or whatever. So I've got heat that's going to move this way. Right? And that's that big Q right there that we're using in the thing right there. Now, what I'm trying to do is to catch some of that and turn it into work going off this way. I wanted to divert some percent of that. I'd like to turn all of it. You know, if you could put gasoline in your car and burn that gasoline and turn 100% of the gasoline's energy into pushing your car down the road, that would be fantastic. With a gasoline car, it's only about 25% efficient. So if you put $4 of gas in your car, you only get $1 worth of motion. Where's the rest of it? It's right here. It's in the change in energy. The water in your engine, they pump water through there to cool it off. That gets hot. The radiator gets hot. It blows that hot air down the road, right? So that change in energy right there is the heat, the waste heat, the exhaust heat if you want. Well, sometimes it's stored in there, but you know, I either store it or I exhaust it. Somehow I change the temperature of something, but I did get some work out. Again, with a car, this is about 75% right here, and 25% of the energy that you put in is actually gets turned into pushing your car. It's not very good, is it? It works good enough, I guess. If you go to an electric car, those numbers switch around. Of the energy that you actually put into the automobile, into an electric car, about 75% of it turns into work and 25% turns into heat. So that's better, right? That's 3 times more efficient. The efficiency of this one is 75%. The efficiency of this one would be 25% of all of it turned into work. So it just depends on the system, and we like to find things that are more efficient and better for the environment, better for the world, cost less, you know, whatever. But that's a nice picture. We'll keep coming back to that. There are some extra little details here that I should mention. T1 would be the temperature of the hot side. T2 is the temperature of the cold side. And the bigger that temperature differential is right there, then the more that you're going to get heat flow, right? If I have a big temperature here and a small temperature here, I'm going to get a lot of heat flowing. And when I have a lot of heat flowing, then I get more, I can divert more of that into work. So that's something that we'll look at when we talk about efficiency and how to calculate that. Okay, Q1 is the amount of energy, the amount of heat that's traveling from the hot side to the object that's turning heat into work. We call that a heat engine. All right, the engine of your car is a heat engine because it takes heat, burning gasoline, and turns it into work. So anything that takes heat and turns it into work is called a heat engine, and Q1 would be the amount of heat that travels from the hot side to the heat engine. Q2 would be the amount that travels from the heat engine to the cold reservoir there. But work is what comes out right there. And that's, we want to get some work, right? Here's some other heat engines. You got your car engine here. I don't know if you've ever seen one out of a car before, but that's kind of what it looks like. And you got the transmission back here, so that's not really part of the heat part of it. But here's a little steam engine. We had one of these when I was a kid. Little toy thing, sits on a table. You take a little block of this white crystal stuff that'll burn, and you put it in a little drawer here, and you set it on fire, and that's going to heat up this tank, which is full of water. The water's going to boil, and that steam is going to come down through a pipe and push this piston up and down, which is going to turn this wheel around, and then the steam gets returned. Sometimes there's a little whistle, and you can pull it and blow the whistle, and maybe there's a belt that comes over here and turns a saw blade or a lathe or something like that. They have some of these at the State Museum if you want to go see them, and you can get on eBay or Amazon or something and buy one. They're kind of fun to play with. You could build one. There's lots of plans to build them online. But the old steam engine is a heat engine, just like your car engine. Here's another little toy that we had when I was a kid. We called it a dinky bird, but everybody else seems to call it a drinking bird. You can buy one of these. Go pull it up on YouTube if you want to see it in action. Terribly exciting. Not really. You take your hand and you put it right here on the bulb. This is all glass, and there's a liquid right there. And so you put your hand here, it heats that liquid. As the liquid gives the heat to the gas, then it's going to expand, and it pushes up here, and there's a special tube that comes and displaces some of this liquid upwards into the head of the bird, and the thing dips over here and appears to drink some water, which cools it off, and it swings back, and it'll sit there and do that slowly throughout the day. Okay, that's a heat engine. You took the heat from your hand and you put it into the heat engine, the bird, and it moved. You got work out of it. Here's another heat engine, I guess you could say. We eat food, put it in here, it comes down into the belly, and we get the caloric value, the heat value out of that, and that food converts into work. We ride our bike or go play tennis or split wood or whatever it is that we're doing. I think you could say that we're a heat engine. All right. Now, for the rest of this, I kind of want to think about a chamber, a little piston in a cylinder, and we've got some gas trapped in here. So, you know, anything would work. A balloon would work. And but imagine all those gas molecules in here, and we've already seen that they're moving really fast, like at rifle velocities. And so when they come up here and hit this thing, they're going to put some pressure on that and push it up. It may be that they have enough pressure to actually lift that piston and expand the volume within here. That would be a volumetric expansion. The gas is doing work. Please remember from first semester physics that work was equal to force times distance. So it's certainly putting a force on there. It doesn't hurt to remember that pressure equals force divided by area. So if I want to find the force right here, then all I got to do is say pressure times the area. And the area would be the bottom of this thing right here. I've got gas that's bumping up on that thing. When it collides right there, it puts a force over this area. I've got a pressure there, but I have force, and it may be that I push this thing up some distance x right there, and if I do move it, if I change its distance, then I've done some work. Okay, and that's good. The piston could be raised. Maybe I reach over there and pull the piston up. That's going to take some work out of me. So we kind of use a sign convention here like we do everywhere else. If I walk to the right, I call that positive. If I walk to the left, I call it negative. Same way here. If the gas does some work, that's a good thing. That's positive, and it pushes it up. On the other hand, if I have to do the work, that takes it out of the whole. So it takes it out of my thing. From my point of view, I have to expend energy. That's negative. We don't like that so much. So maybe I pull the piston up. Maybe I push it down. That changes the volume. We know from the ideal gas law that if I change the volume, that's going to change the pressure and the temperature. Or if I heat this thing, maybe I add some heat into it. As I add heat, that's going to change the pressure, which could change the volume, and that could change the temperature, which could change the pressure, which these things just go back and forth. But the ideal gas law ties all that together for us, and we can see what happens. Okay, so that's a useful idea to kind of picture to have in your head. We could add heat. There's my Q right there, and as I put that in, this could heat up. So there's my delta U, and I could push this thing up, which gives me some work. But rest assured that the change in internal energy plus the work has got to be equal to the heat that I put into there. I'm not going to get work for free. I'm not going to get change of internal energy for free. I have to pay for that by putting gasoline in my car or wood in the stove or something, right? I got to make that happen. Okay, I got 4 different processes here I'd like to walk you through real quick. This first one is called an isobaric process. And when I say process, I really mean a set of steps that kind of happen in a particular way. So this word isobaric is interesting. Iso means some. I'm sorry, not some, same. And baric refers to pressure. When we look at a barometer, we're reading the pressure. When we look at if we talk about the barometric pressure today or something like that. So same pressure. Delta P equals 0. My pressure didn't change, so there is no change of pressure, right? When you see a process, when you see heat added or an expansion or whatever on one of these little cylinders like this, and the pressure stays the same, then you know you're looking at an isobaric process. And we have a formula over here that says, how much work am I going to get out of that? And it's real simple. You take this constant pressure. Let's just make up a number here. Let's say that the pressure is 200,000 Pascal. And you multiply that by the change in volume. Maybe this thing goes from 0.3 cubic meters to 0.4 cubic meters. So then I could come in down here and I could say my pressure is 200,000 Pascal. My change of volume goes from the final to the initial. That would be 0.1 cubic meter. Multiplying by 0.1 is going to take a 0 off. So I get 20,000 Pascal cubic meters. And of course a Pascal is really a Newton per meter squared. So the meter squared here cancels 2 of these. I get a Newton meter, and a Newton meter is a joule. The work that I just got out of that is 20,000 joules of work. Okay? So that's pretty good. We just got some stuff done. Down here are some of the gory details of where that work equals pressure times the change in volume comes in. Work equals force times distance. Remember that force is pressure times area. If I take that A and scoot it over with the D, then it would look like that. And area times the distance, the area of the bottom of this cylinder where the pressure is pushing, times the distance that I move it, would be this volume between the old bottom of the piston and the new bottom of the piston. That's that delta V right there, that added volume from moving the thing up. And that's simply V2 minus V1. So that's where Either one of those that you like is fine. It works both ways. All right. But that would be an isobaric pressure, isobaric process. It all happens at the same pressure. Okay. Now it doesn't have to happen at the same pressure. Other things can happen, but in that process, the pressure is always the same. Now here's process number 2. This is called the isochoric process. Iso again means same. Looking for the pencil point. Can't get it to the right. Where is it? There we go. Come on. Almost there. Wow. Okay. Same. I like to remember this as core volume. Choric. That's not really where that comes from, but it kind of ties it together in my head. The same volume is what we're looking at here. There's no change in volume. Well, that would be like if I'm adding heat in here and I've got my finger sitting on top of this thing, not letting it move, right? And if I hold that thing down, then this doesn't move. That means that my delta V equals 0. When I think about work, work is force times distance. If the distance is 0, why then the work is 0, right? So I'm not going to get any work out of an isochoric process. If you don't move the piston, you don't do any work. And that's the thing there. What would that look like? I've got this little pressure volume diagram here. These are pretty important. I didn't stretch this one down, resized it to 16 by 9, but forgot to stretch that one down. Pressure on this axis, volume here, and that's the way we usually do it. Right here, the volume is constant. It is always this number right there. So all it can do is either go straight up or straight down. If I add heat into there, then the pressure is going to go up, up, up. And if I cool it off, if I remove heat, then the pressure is going to fall. But that's all it can do, straight up or down. How much area is underneath this curve right here? Well, none, right? The area underneath these curves gives us the work. Look at this one back here. Here's another PV chart. This time the pressure went straight across. There's that constant pressure. Here's the volume. We took this number times this number, and it gave us the work. What is that? Pressure times volume would be the area that is trapped inside here, the area under the curve. Those of you that have had 10 cents worth of calculus know that the area under the curve is an important calculation, right? We do the integration to get that. So we can get the work here. This one is a simple rectangle, so we multiply the pressure times the change in volume, and we've got that. That gives us the area under the curve. When I look at this one, and I say, what's the work? What's the area under the curve? It has height, but it has no thickness. So whatever the height is, times 0 is 0, and I never get work out of an isochoric process. If you don't move it, you don't get any work. If x equals 0, force times 0 equals 0. All right. Now, if I bring that back to the first law, right here I've got the first law of thermodynamics that we were talking about. And this is kind of a neat thing to do. If I bring it back here and I say, well, I just found out that the work in this case, in the isochoric process, is 0, then see how all of that heat had to go into the internal energy? And we've already said the temperature of it goes up and the pressure of it goes up. So that's where that's stored. Those gas molecules inside that trapped volume are moving more now. They have more kinetic energy. And that's where that thermal energy, that internal energy, whatever you want to call it, it's all in the kinetic energy of those molecules moving around. They're bouncing off each other more violently, off the walls, everything. So in an isochoric process, you can find the work and then put that into the first law right there. Here's the third process called the isothermal. And you already know by now that iso means same. And it's not too hard to figure out that thermal is referring to temperature. So these are processes that happen at a fixed temperature and they don't change. That could happen by either adding just enough heat to keep it the same temperature or make it happen very slowly. Now, when I look at this cylinder over here, let's say that I reach over here and grab the handle and pull this thing up. So I've got a delta V that's increasing. That's going to make the pressure drop off here of the gas inside here, and it could make the temperature fall as well. Remember, ideal gas law says the pressure and the volume and the temperature are all tied up, and you change one, you usually change the other two as well. I don't want to change the temperature, so that's where I come in with a little flame under here and surround the chamber with a constant temperature heat reservoir. That's going to add a little bit of heat. I can put a little fire under there. Or if I do this super slowly, then I don't get a rapid expansion. Rapid expansions cause drops of temperature. Try this for me. I'd like you to take your hands out in front of your face and imagine that your hands are cold. It's winter time. Your hands are super cold. You want to warm them up. So you take your mouth and go and you breathe with your mouth big wide open, and that air comes out and warms up your hands. Now imagine that you're holding a bowl of hot oatmeal. You want to eat your hot oatmeal, but it's too hot, so you're trying to cool it off. Now you're going to blow on it again, but this time you're going to purse your lips and make a little bitty hole there and blow the air through that little hole, and the gas is going to come out of your mouth and rapidly expand and cool off, which will cool off your oatmeal. All right, we do this all the time, but it doesn't mean we think about what we're doing. Rapid expansion causes cooling, so if I do this very slowly, then I don't get that cooling. All right, so either way works, but the isothermal process, I want delta T to be equal to 0. Now, here's some more little steps that we can do right here. If delta T equals 0, then I'm not changing the internal energy of this. Remember that the average kinetic energy was equal to 3/2 kT, right? According to kinetic theory. So if delta T equals 0, then delta KE equals 0. I'm not changing the internal energy there. And going back to the first law, Q equals delta U plus W. Now we're saying that delta U in an isothermal process is 0. That means that all of the heat that I put in there goes into work. So when I put this little fire right here, then I get some work. And the amount of work that I get is equal to the amount of heat that I put in there. Okay. That PV chart, that pressure-volume relationship would look like this. I'm up here at the start, and I'm doing one of two things. Either I'm adding heat very slowly, and that's going to make the pressure lift this just a little bit, so my volume is expanding, but the pressure is going to drop. Remember, I'm keeping temperature constant here. Plan B, I'm coming in here and lifting this by my hand and adding a little bit of heat to keep it going. Or maybe I'm doing it super slowly. As I do it, the volume expands, but the pressure is going to drop as I do that. I'm doing it slowly enough to where the temperature doesn't drop as well. Okay, so that's a possibility. Now there's one more direction you can go with this thing, and I'm trying to show you all the different avenues that you have, because when you step up to one of these problems, you need to go, oh, this is isothermal, so I know that all the heat turns into work. Or maybe, they ask about the pressure and the volume. That's an ideal gas law problem, so don't forget about ideal gas law. Here's what used to look like right there. But now we're saying the temperature is the same. That means that T1 equals T2, so these are going to cancel out, and I'm left here with Boyle's law to do. So maybe you need to step into ideal gas law. Maybe you need to take the ideal gas law and substitute it into something else to get to where you want to be. All right, but having all those pieces out in front of you is kind of a nice thing to do. Being familiar with the different formulas here. Okay, one last process here. This is called the adiabatic process, and in the adiabatic process, there is no heat that goes into or out of the gas. So this is an isolated system, an insulated system, and we are not letting any heat go in or out of this thing. Possibility A, it's super good insulated, like that, so that no heat can come in or go out. Or possibility B is that this process happens very rapidly, very fast, and there's just not enough time for heat to come into the thing there. So the isothermal happens slowly, and the adiabatic tends to happen quickly, or very well insulated. All right. Now all these are ideal cases, and real life is a little bit more messy than this, but these are the four we want to look at. Okay. Q equals 0 is the big thing here. So going back to the ideal gas law, the first law of thermodynamics, if Q is equal to 0, then I've got this, and I can solve it for either delta U or W and find out how much work I get out of this process here. This thing is expanding. That's an X. There is a force coming up here, so I'm getting some work. How much work do I get when that thing moves? Well, it depends on, I didn't build a fire under it, so I didn't add any heat. I still have to pay for it, so I have to pay for it out of the internal energy that was already in there. And the internal energy of the gas is going to drop and push the piston, so I get some work, and I just turn it, that stored energy that I already had, turn that into work. All right, that's the adiabatic process. Now, those are tricky to keep track of, so I've made up this little cheat sheet that I wish somebody had shown me when I sat through this the first time around. Here are all four processes, and I've got them on the graph there. Remember that the isochoric means the same volume, and so the volume is constant. It goes straight up, or it can come straight back down. These things can travel either direction, but they got to stay on that line. If it's isochoric, the pressure's going up, the pressure's going down, but the volume is not changing. It's fixed right there. Okay, adiabatic, the Q equals 0. I'm not adding any heat right there. Isothermal, delta T equals 0. Isobaric, delta P equals 0. I'm not changing the pressure, I'm not changing the temperature, I'm not changing the heat, I'm not changing the volume. All right, so this little table kind of hopefully helps keep that straight. Maybe you want to put fast and slow on here, something like that. It's not always true, but generally. The variable here, Q equals 0, delta T equals 0, so delta U equals 0, delta V equals 0, so the work equals 0. And then what that means in the ideal gas law and in the first law of thermodynamics, right? Kind of all the implications of when they tell you it's an isochoric, you know there's no volume change. That means delta V equals 0. If I don't move the piston, then I didn't do any work. And if I didn't do any work, then in the first law, you know, these are the only two things left. There probably should be a negative sign in there. Okay? No, I guess that one's okay. It seems like somewhere there's a negative sign I should have put. I think it's this one. I lose energy, and that gives me some work. Okay, anyway, go think about those for a while and try to get this all in one place. I'd like you to know what the graphs look like, and I'd like you to be able to do some of these things. So that's the first law and all the implications with those four processes. There is a second law. The second law can be stated different ways. Here's a couple of them right here. In the first statement there, the Clausius statement says heat cannot by itself pass from a cold to a hot body. You know that heat always goes from hot to cold unless we make it go backwards. If you have a refrigerator, think about what you're doing. You're taking the heat that's inside your refrigerator and you're throwing it outside the refrigerator into your room. Okay? If you run your air conditioning in the summer, you're taking the heat inside your house and you're throwing it outside the house. So it is possible to make it go backwards, but it doesn't do that by itself. All right? Kelvin and Planck came along, had another way to explain the second law of thermodynamics, which is that it is impossible for any system to undergo a cyclic process whose sole result is the absorption of heat from a single reservoir to single temperature and the performance of an equivalent amount of work. There is no way to turn 100% of your heat into 100% of work. Okay? We said the car engine was 25% efficient. That's the best we can do with a car engine. And you know, we can shave off a little bit due to friction or air resistance or something, but in the end we're trapped by this second law of thermodynamics that says you can't turn all that heat into work. It's just not physically possible. Sad but true. All right. Here Beiser wrote a book and he had a little bit different statement. It's impossible to construct a continuously operating engine. That's what it means by cyclic process here. So that's kind of just a when they say cyclic process, your car engine piston goes up, compresses gas, pushes down, then it goes up, down, up, down. It's in a cycle, and that cyclic process is going over and over. Beiser, instead of using the word cyclic process, is talking about a continuously operating engine. Same thing. All right. Anyway, it's impossible to create something that takes heat and does an exactly equivalent amount of work. The efficiency is always less than 100%. You always have energy scattered off, loss to friction, air resistance, leaks, goes into your radiator, goes into your, blows air past the coils and pumps that into the cabin of your car to heat you up in the wintertime. Okay, but it didn't go into the efficiency of your engine. It didn't push you down the road, but you are getting a second use out of it, but not work. Okay. Hope that kind of makes some sense. Here are all three of them one more time. Not sure what that thing in the middle is. That is the first law, which should have gotten shoved down here to say Q equals delta U plus W, but it doesn't. Sorry about that. But there's all three laws of thermodynamics. One last little thing kind of for fun here. I had a teacher at Clemson that taught us statistical thermodynamics, the probabilities of each molecule, what it's doing at any given time. Loads of fun. And he was a big-time poker player, and he had an analogy of how thermodynamics is like poker. According to him, the Zeroth law, which says that if A equals B and B equals C, then A equals C, everything is in the system. Everything in the universe, the sun and the earth are both in the system. They are not at the same temperature, and so heat is coming from the sun to the earth. It's moving towards thermal equilibrium, and one day will be at thermal equilibrium. We'll all be at the same temperature. Okay, we cannot get out of the game. We're stuck in the poker game. According to him, the first law says you can't win, right? If you go to Vegas and drop a quarter, pull the lever, and you win $500, you just got something for nothing. And that never happens in physics. If you put a quarter in, you might get a quarter back, but you might get a dime and 15 cents gets lost to friction or something. Okay? You are never going to get something for nothing in the real world. According to him, the second law is you always lose. The efficiency is always less than 100%. There's this quantity which we haven't talked about called entropy, but basically it's a measure of the order in the universe. If you take a log, right, cut a piece of wood or something, coal, gasoline, oil, whatever, that has chemical structure. It has chemical energy stored in it, and then if you burn it, that chemical energy is converted into heat energy, but you never get the log back, right? And so entropy measures how much stored structure, energy, potential energy, whatever you want to call it, and how that order, how long it took the tree to grow, you've lost that now. You gained some heat, but you got to go grow yourself another log because you can't burn that one again. All right? So those are just some kind of fun ways to think about the laws of thermodynamics, and I hope this kind of made sense for you, and we'll be back next time.